All right, Matt 2, here we go. We've got prisms and cylinders. We're going to be looking at the surface area and the volumes of solids during this unit. So we're going to start with the basic ones, prisms and cylinders. So here we have a prism. So a lot of people think of it just as being a box. So we want to find the surface area. That's the outside of the shape. So like if this were a cardboard box, the surface area would be the cardboard part of it. And then the volume is like the empty space that you can fill up the box with. So if this is a cardboard box, the surface area is the cardboard on the outside. The volume is how much stuff you can stuff into that box. So looking at this one, it's all done up in unit squares here. So this length over here is 4. This length back here is 3. And then this part right here is 2. So when we're looking at the surface area, remember this is the cardboard part of it, if this were a cardboard box. On the top and the bottom of the box, which I can't see that's covered, I've got 4 by 3. So the area of the top and the bottom should be the same. And there's 2 of them. There's 2 4 times 3s. So that's the area of the top of the box. Then I've got the front of the box and the back of the box, and they should be the same. And those are 2 by 3. And then I've got the right side of the box and the left side of the box. Here I've got 4 by 2, so that's this side, and then the other side should be the same as that. So those are the 6 sides of the box, top and bottom, front and back, left and right. So I got 2 of the top and bottom, I've got 2 of the front and back, and then 2 of the left and right. So we're just going to add those areas together, and that would be the cardboard part if this were a cardboard box. So 12 times 2 is 24. 6 times 2 is 12. And then 8 times 2 is 16. So we got 24 and 12 is 36, 36 and 16 is 52, yeah, 52. And then since this is area, we would be calling it units squared. The volume is how much we can fill up the box. Now all major volumes, formulas, well not even the major ones, volume is the area of the base and then you fill up that base. So like if we said that the top was our base here. So let's say this part right here. Here's the area. And then what we do is we fill it up using the height. So it's really saying how many areas fit in to this box. So I've got an area, a base area of 12 up here. So I start with my base area. And how many of those base areas are going to fill up that box? Well, I've got 2 of them. I've got one on the top and a second one on the bottom. So that's the height. So I take my base area, and then how much of that base area is going to fill up the box? How many of those base area blocks are going to fill up that box? There's 2 high. So it's the times the height of 2. So it's pretty simple. All we have to do is do 4 times 3 for our base area, and then multiply by the height of 2. So 4 times 3 is 2, times 2 is 24. 24, and then this would be in units cubed, because I've got 3 units. I've got a length, a width, and a height, all of them having a unit designation. So this would be in units cubed. All right, next. This is also a prism. This is called a triangular prism because the bases are triangles. So this one we would have called a rectangular prism because the top and the bottom were rectangles. Now in a prism, we always have these parallel lines that connect the 2 bases. So I got a base on top, base on the bottom. Now remember that the base does not mean top and bottom. Base means that it is connected by these parallel lines. On the previous problem, I could have said that this side over here was my base because it's connected by these parallel lines here. to the bottom part, which would be on the back here. I could have said the front is my base because parallel lines connect it to the back. So we could have done anything as the base. Base does not mean top and bottom. Base means that it's connected by parallel lines for a prism. So surface area of this prism, oh, we're supposed to mark all the side lengths of the prism. I've got 3, 4, and since it's a right triangle, we should know by now that this is a 3, 4, 5 triangle. It's a Pythagorean triple. On the bottom, this would also be the same triangle, 3, 4, and 5. And then our heights over here are the parallel lines that are connecting the two bases together, and they're all going to be 9. So that's 9, and this was 9 over there. All right, so we've marked everything on there. Check. Part B, find the surface area of the prism. So if this were a weird cardboard box, we would have 1, 2, 3, 4. We'd have 5 different sides to it. I'd have a top base and a bottom base. Both of those are triangles. So my surface area would include 2 triangles. That takes care of the top and the bottom. And then over here on the side, I've got 1 rectangle. On the back, I've got 1 rectangle. And then this big front part is a 3rd rectangle. So that's how I'm going to find my surface area. I'm going to look at all the separate shapes that make up the outside of this prism. So my 2 triangles are exactly the same. Triangle formula is 1/2 base times height. Remember, base and height are perpendicular to each other. So this would be 1/2 of, why did I put 1/3? 1/2 of 3 times 4. Base of 3, height of 4. So that's the 2 triangles, 2 of the 1/2 3 times 4s. Then I've got 3 rectangles. Let's start with this back one over here. This rectangle back here in the back is 3 times 9 for its area. So that'll be 3 times 9. This rectangle over here is going to be 4 times 9. And then the front rectangle here is going to be 5 times 9. And there's all my areas. I've got 2 triangles and 3 separate rectangles making up this shape. Half of 3 times 4, 3 times 4 is 12, half of that is 6, and then 2 times 6 is 12. So the triangles have a total area of 12. My first rectangle has 27. My next rectangle has 36, and then 45. So if I add all of those areas together, I get 81, 88, 108. I get 120. And this would be in centimeters squared. All right, now let's find the volume of the prism. Like we said before, in the volume, we're going to look at the area of the base. Our base is a triangle because it's a triangular prism. And then I'm asking myself, how much can I fill up that shape with that base? So I'm going to take the area of the triangle and fill it up 9 times because that's the height. So we're going to do volume equals, the base is a triangle, so that's 1/2 3 times 4. We did that right here. There's my base area. So it's base area times height. My height is over here at 9. We're taking our area and filling it up 9 times there. So 1/2 3 times 4, that would be 12. Half of 12 is 6. We'd get 6 times 9, which is 54. So our volume is 54 centimeters cubed. Why is it cubed? Because I had 3 centimeters, 4 centimeters, 9 centimeters. That's 3 different centimeters that I'm multiplying. That's why it's centimeters cubed. Next, here we've got a regular hexagonal prism. This one has a base that is a hexagon, and then I've got a hexagon on top. And then these are the sides that are parallel to each other, connecting the two bases together. So looking at this surface area, on the top and the bottom, I've got regular hexagons. So I got two regular hexagons. And then all around the sides, I've got 6 rectangles. And it looks like they're all 4 by 7. Since this is regular, all these lengths are exactly the same. So I've got one here, one over the side here, one in the back there, one over on this side over there, and then one on this side there. So I've got 6 of those. So plus 6 rectangles. Remember, this would, if it was a cardboard box, this would be the cardboard portion of the box. All right, so we just need to find the area of the regular hexagon. Remember, we did the apothem and then half the side length. And then to do this, we found our central angle here. We'd do like 360 divided by the number of sides. We'd get 60 degrees. And then the apothem cuts it in half, so this is, I almost put to 60. That's 30 degrees right there. And then this is half the side length, so this is 2. So this is a 30, 60, 90 triangle here. So the apothem, if this is 30 and this is A, this would be A root 3, so this would be 2 root 3 for this side. So my apothem is 2 root 3. I'm now ready to write my regular hexagon area. There's 2 of them. And the formula for a regular hexagon that we talked about earlier was 1/2 the side length, which is 4, times the apothem, which we just found out was 2 root 3, times the number of sides. It's a hexagon. There's 6 sides. All right, so there's 2 of those. This is the area of the regular hexagon here. And then as far as the rectangles, there's 6 rectangles, and all of these rectangles are 4 by 7. So there's 6 rectangles that are 4 by 7. So over here, I've got my area of my hexagon. Half of 4 is 2. 2 times 2 is 4. 4 times 6 is 24. So I get 24 root 3. That's the area of the hexagon, and there's 2 of them. Over here, I've got these rectangles, and they are 4 by 7, so that's 28. So 2 of those, that's 48 root 3. 6 times 28, 168. There you go. There's my surface area. We can't combine these. These aren't like terms. So the exact answer would be this in centimeters squared. Now, if we wanted to take our calculator and find out what this is approximately, I would say 48 square root of 3 is this, and then I'm going to add 168 to it. So it comes out to about 251.1. Sounds good. So this is approximately 251.1 centimeters squared because it's area. Volume. Volume would just be the base area times the height. We're going to find out how big our area is on the bottom and then fill it up with this height 7 times. So our volume is the base area, and we already had our base area right here. It was 1/2 4 times 2 root 3 times 6. It came out to 24 root 3. So our base area times our height. We already found the base area over here. It's 24 root 3. And I'm going to multiply by the height of 7. And 24 times 7 ends up being, is that 168 again? Oh yeah, it is. It ends up being 168. So we get 168 root 3 centimeters cubed this time. Oh, this is inches. Sorry. Pretend like I wrote inches there instead of centimeters. And this is approximately, comes out to about 291. right, surface area of a cylinder. Okay, so surface area of a cylinder, you kind of have to do a little pretending here. I can tell that the top and the bottom are circles for the outside of it. So surface area is going to be 2 circles. So that's pi r squared. But then what about this section that's going around it? So like if this were a can, this would be the aluminum around the outside of a can. Well, if I make a cut right along here and then unroll this, that would end up being a rectangle. Where this is 8. So I'm cutting down here and I unroll this thing, kind of visualize that we cut it along here and we've unrolled it. And what we have here is this top part up here, that's actually this part right here. And that is the circumference of the circle. And we found out circumference was 2 pi times r. So this rectangle that represents the, the side of this can or cylinder or whatever it is, it's a rectangle if you cut it out, and the top of the rectangle is the circumference of the circle there. So this is going to be plus the height times 2 pi r, the circumference. So we've got the 2 circles, and then the rectangle is the height of 8 times the circumference. All right, so work this out. We've got 2 pi r squared, pi times 5 squared, plus the height of 8 times 2 pi times the radius of 5. So 25 times 2 is 50, so I get 50 pi for that part. Now this is 10 pi. 10 pi times 8 is 80 pi. These are like terms. We can combine them. We get an exact answer of 50 plus 80 is 130 pi. And this would be units squared. And that comes out to approximately 408.4. If we do the volume is just going to be the base area, so the circle on the bottom, and then how much are we filling it up? We're filling it up by a height of 8. So this would be the base area, which is pi r squared, times the height. So we would do pi times 5 squared, and then multiply it by the height, which is 8. So this is 25 pi times 8. There's the base area, multiply by 8. That would be 200 pi. And this would be in units cubed. And 200 pi is approximately 628.3 units cubed. Did I put squared? Cubed. There we go. All right, we're almost done. Now we get to Cavalieri's principle. So this is called an oblique cylinder. It's when the sides aren't perpendicular over here. So you can see this is kind of like leaning. And let's just say that this section over here, this leaning section, let's say there was 9. Sometimes we call that like a slant height, so because it's slanted. Oops, wow. Slanted. So that's a slanted height. All right, so how are we going to find the area if this cylinder is slanted to the side? Well, imagine if this were a stack of pennies, and then you just kind of tapped the stack of pennies so it leaned but didn't really fall. There's still the same amount of pennies there. So there's still the same amount of pennies, so the volume shouldn't have changed just because it's slanted. And so what we find out with Cavalieri's principle is that when you have an oblique or slanted cylinder like this, the height is always going to be counted where it is perpendicular. So even though this 8 over here isn't part of the shape, this is the height that we're going to use to calculate the volume. We do not use the slant height. We use height that is perpendicular. So whenever we refer to height, it is always perpendicular to the base. You cannot use a slanted height in any of your formulas. So it's still going to be volume equals base area times the height, but we have to remember this is the height that is perpendicular to the base. So we can't use this slanted height in our volume calculations. And this ends up being the exact same formula, even though it's slanted, as the previous problem, because it has a height of 8 and a radius of 5. So we're still going to get 200 pi on this one. Using pi r squared 25 pi for the area, and then multiply by 8. So oblique solids like this will always use a height that is perpendicular to the base, even though it's not actually part of the shape. Last one. Henry needs to replace the hot water tank at his house. He estimates that his family needs a tank that can hold at least 75 gallons of water. Okay, so he needs 75 gallons. All right, but the tank has to fit in a small closet. Oh, that's too bad. His local hot water tank supplier has a cylindrical model. Okay, cylindrical. So if we're looking at volume, it's base area times the height. And since it's a cylinder, this is going to be pi r squared times the height. Okay, so it's cylindrical. It has a diameter of 2 feet. Diameter is 2 feet, but our formula uses radius, so I better write the radius is 1 foot. And the height is 3 feet. Height is 3 feet. I got everything I need. I need a radius, got it. Height, got it. Oh, I can find my volume right now. Let's look at the volume. Volume would equal pi times r, which is 1, because diameter, it's half the diameter, and then times the height of 3. So this is just pi, 1 pi. 1 pi times 3, 3 pi. So it looks like what they're trying to sell me has a volume of 3 pi feet. And what is 3 pi? 3 pi comes out to approximately, how do I want to round this? Let's do 9.425 feet cubed. I got a little bit of a problem here. This is in feet cubed and this is in gallons. Let's keep on reading, I guess. If 1 gallon of water is approximately, oh, here we go. 1 gallon is 0.1337 cubic feet. That's elite. So I know that 1 gallon is the same as 0.1337 cubic feet, so that's feet cubed. All right, so I have to do a conversion here. I'm starting with 9.425 feet cubed. I want to convert it to gallons, so I need gallons on top, 1 gallon on top. And that's equal to 0.1337 feet cubed. So doing this, the feet cubed cancels, and I have just gallons left. So that's my new units. So that would be 9.425. Now we're in gallons, because I cancel it out cubic feet. And I'm going to divide by litre. 0.1337. All right, calculator, what is this going to end up being? So when I do 9.425 divided by 0.1337, I get 70.5 gallons. Not enough. We needed 75 gallons, and this tank only provides 70.5 gallons. Got to get a bigger model. All right, that's all I got. Math hard. See you guys later. Bye-bye.